Ahmed. Okay, first of all, so I would thank to the organizer for this opportunity to talk a little about my works, including myself, of course. So my talk will be about generally about some obstacle problem or variational inequalities and corresponding Lewy-Stampacchia inequalities. So my talk will be in two parts. The first part, I will try to give a brief introduction about the stochastic calculus and the introduction of stochastic or noise generally in PDEs. So let me start my talk by mentioning some motivations, and I will start by very basic example. So if you consider, so for example, the following model of population growth, where you have NT is the size of your populations, and you have AT is some coefficient, which is like the relative rates at time T. But as you know, that generally in our application in real life, we don't, there are too many uncertain quantities that we don't take in considerations, which bring some random environmental effects. Therefore, it would be better to consider AT taking the following form, where RT some deterministic part and adding some noise in some appropriate sense. So generally we know only some probability distribution of some parameters, and therefore it is like mandatory to consider the following general form. And then the question is how we can deal with this kind of problems and what kind of noise that we can consider to be in appropriate mathematical formulation of the problems. So the stochastic calculus is one of the tools that can answer this kind of questions. So you see that if you add some randomness to some phenomena, you will get more realistic mathematical models. This is concerning some ODEs. Now I will try to go to the PDEs, and basically I will try to focus in fluid dynamics, since there are many people interested in this phenomena. So like the incorporation of stochastic or noise in fluid dynamics is mandatory or very necessary to mimic many real phenomena. And you see, there are many reasons. The first reason that push you to go forward stochastic calculus in fluid dynamics, it's like the complication and the chaotic behavior of fluids, and basically what we call a turbulent phenomena. And this is generally, we don't know exactly, therefore you have some uncertainty, and this leads you to go to the direction of stochastic calculus. Generally, when you try to build some model from real applications, you have some statistical approach you have some experimental data, therefore you will use some statistical approach, and this kind of approach lead more to stochastic model, not a deterministic one. And you can find the literature many studied in this direction. Let me mention the following. If you consider the system of Navier-Stokes equations, generally, if you consider some Lagrangian formulation of the problems, then you can split the velocity field into some of two components. The first one is the slow oscillating, which is basically the deterministic part, and some fast oscillating, basically related to the turbulence and should be a stochastic part. And this, when you consider this, when taking this into consideration, you will derive some Navier-Stokes equations in Eulerian coordinates, in addition with some multiplicative noise dependent to the velocity and the gradient of the velocity. And therefore, we need to develop some mathematical theory and foundation for stochastic PDEs in fluid flow. More classical application of stochastic, when you are interested to do some numerical simulation, you have always you need to deal with some stability issues and the convergence of scheme. And since in the first stage of the modelization, you are ignoring some parameters, this became very costly in the numerical experiment. Therefore, when you add in some uncertainty, you are in somehow compensate the difference, and it's a very efficient way. In the last year, there are also kind of what we call regularity by noise. there are some deterministic problems that we haven't generally the well-posedness, but when we add some noise, we can prove the well-posedness. And by well-posedness, I mean the existence and uniqueness. For instance, if you have some system of ordinary differential equation with very non-regular function f, for example, if you consider some dy t equal f ty, if f it is not continuous and nor an infinity, you can't prove the uniqueness of solution. But if you add some noise, you can prove the uniqueness, and there are very recent results in these directions. Another thing that, for example, if you consider the transport equations, you can avoid the explosion of the solution in brief time with large probability if you add the noise. And you can find the literature many other motivations. So if we take in consideration all this criterion as consideration, the stochastic calculus would be some necessary tool to study some realistic model. And I will conclude by the following very classic example. Generally, when we solve PDEs, we can't solve explicitly the solutions. And this is, for example, if you are considering the following problem, if you are trying to find some harmonic functions, satisfy some Dirichlet condition in the boundary. Generally, you can prove the well-posedness of this kind of problems, but you haven't explicit formula for the solutions. And Kokotani in 1944 proved that the solution can be explicitly by using some stochastic tool, and the solution f will be like the expected value of f of the first exit point from E of the Brownian motion start at the point X, which belongs to your domains. Then this kind of result can generalize, and you can study more semi-elliptic or semi-parabolic partial differential equation by considering more general stochastic process, which called some diffusion process, more general than Brownian motion, to write the explicit formula by considering some conditional expectations. So all those are good reason to interest in stochastic calculus. So let me now try to tell you a little about some basics. So I will consider some complete probability space. Omega is my sets and F is my sigma algebra of the event, and I have some probability measures. I will take generally some random variable if you want taking value in some separable Banach spaces. For instance, you can think R or RD, but I can go in infinite dimensional settings. Separable is important because I don't need to deal between the weak measurability and strong measurability, since they are equivalent in separable Banach spaces. So what I code by random variable is some measurable mapping from my set omega endowed with my sigma algebra F, which take value in some separable Banach space endowed with the Borel sigma algebra. What I mean by stochastic process, it is the family of random variables. So you see at every omega, I associate a mapping indexed by T, and T will be some parameters. The set E may be a discrete set or continuous set, and generally it's be like the time intervals. Then I code stochastic process is continuous if the following map T associated the image xt omega is continuous for every omega or almost solely omega. And then you have a very, very interesting notion, which is the notion of the filtrations. What I mean by filtration is some increasing family of sigma algebra, subset of my initial sigma algebra. This filtration is very important because it's allow me to consider some chronological order of my events for my stochastic process, and it is very important when you are constructing some stochastic integral. You can consider as example as sigma algebra, the filtration, the sigma algebra generated by some process itself. And therefore, you will see that my process will be measurable with respect to the sigma algebra. Therefore, I can say more And I can talk what we call the adaptness or measurability with respect to the filtrations. If I consider my filtration, my process, which is depends to two parameters T and omega, and let's say take value in Rn or generally in some Banach space E, is called FT adapted if the following map for every omega associated xt omega is FT measurable. This gives some correspondence between the randomness and the time, and force my process to behave in some way. I don't allow to my process to behave in very, very chaotic way, and it should respect this this measurability. Otherwise, I can't construct the stochastic integral or give sense to what happened. So I can also go to what we call some predictable process, which is our more general than FT adapted process. And predictable is like more or less like adapted, but with some additional properties. And it is more appropriate for the study of partial differential equations. For instance, if you have some continuous process in time, and adapted to with respect to my filtration, then I can prove that I can find some predictable version of my process. Okay, let me now go to the very basic stochastic process, which we call a Brownian motions. The Brownian motions is some map defining from 0 infinity take value in R. And by the way, I am talking about the Brownian motion in 1D. So it is continuous in time. So at almost 30 in omega, the following map T associated omega WT is continuous. And I start from 0. And one of the very important properties is the increment of Brownian motion is independent of the sigma algebra generated by the Brownian motion itself until the instant s, the time s. And this is very important, and this gives a very, very basic property for the Brownian motion. I will try to talk a little about it later. And therefore, my Brownian motion is generally a Gaussian measure, and therefore it follows some normal distribution with mean 0 and with variance T minus S in 1D, of course. So I can all generalize that in infinite dimensional system, of course. So I will try to talk a little bit about the properties of Brownian motions. You can prove that almost surely your Brownian motion is at most Holder continuous with some parameter gamma, and gamma can go until 1/2, but can't reach the 1/2. This is very important because if you have this, you know that your Brownian motion is it's not differentiable. This is imply that your Brownian motion is not differentiable. Then if you are trying to write some dw, so you should give an appropriate sense for that. The second thing that you can prove that if you consider some discretization, then the sum of this is convergent to T, means that the square or the square variation of my Brownian motion converges in L2 to T, and T my time. And therefore, you have this, the path of Brownian motion has infinite variations. Okay, from this, we have that the square of variation is converging to T, and by using that, you can prove that the path of Brownian motion has infinite variation. And this is important because now we can't use the theory of Riemann-Stieltjes integral to define the integral because I have unbounded variational functions. And of course, you can prove that it is nowhere differentiable with probability 1. All that reason push you to think to construct some integral with respect to these functions in an appropriate way. So this is just an illustration for Brownian motions. Here I am mimicking like 1,000 trajectories of Brownian motion. This one, for example, is one trajectory. And you see, I start from 0, and you see these trajectories are dense about my mean, which is 0, and I have some variance. If you draw the square root function from above or down, you can find that your Brownian motion is more or less between the 0 plus the square root of t and minus square root of t. And this is correspond to the variance of my Brownian motion. Now I will try to say a few words about the construction of the integrals. So I will consider some separable Hilbert space, and you can always think about R or RD. I will construct integral for this family of processes. And for that, it's classical, like we construct the Lebesgue integral. We can define the integral from elementary functions. Then we can go by using some density argument. But the thing that we need to respect, that if we consider some elementary process, this coefficient will depend to omega, and I will consider my element EG is FTG measurable. If you see here, I have the characteristic of the interval TG plus 1, and my coefficient should be measurable with respect to the initial points. I can't consider any other points, because if I consider different measurability, I will get a totally different things. For instance, if I consider the midpoints, I will recover what we call Starnovich integrals, but when I consider that, I am constructing E2 integrals. So we can prove that my elementary process is belonging to my space that I want to define the integrals. And it is classical that I will put the definition of my stochastic integral as following. Just I have these coefficients, which is FTG measurable, and I consider the difference of two Brownian motions. Since Brownian motion is continuous, this is as well defined. And I can prove that this sum take value in my Hilbert space. This is what we called E2 integrals. Then I can prove the following very, very important property, that I can switch from the stochastic integral to some deterministic by using my expectations. And what I mean by expectation is the integral over my set omega with respect to my measure P. You can prove that by using the basic properties of expectation and using basically the independent increment of Brownian motions. And here, this FTE measurability play a very, very fundamental role to use this property of independent increment. So it is like crucial. When I prove this E2 isometry, I can prove that this property holds for more general class by proving some density lemma. Therefore, I will conclude by the following properties. In my space and 2W0T with value in Hilbert space, the space of predictable process, on do it with some norm T, I can define that by using some density arguments. I can prove that the expectation of the stochastic integral equals 0 if I start from 0. And by the way, this is more or less related that what we call that E2 integral enjoy the Martinger properties. And this class of process is more general, but it is very important property. The third property, it is E2 isometry, and it is very important tool because it helps when we consider the expectation to switch from an integration with respect to some Brownian motion to the integration with respect to time. Of course, I can prove that my map that associate every function in this space is some stochastic integral in time is continuous with value in some Lebesgue space, starting from omega and take value in h, which is linear and continuous. And therefore, I can prove the isomorphism between the two norms by using E2 isometry. Then this is the chain rule, which is very important. Classically, when you consider some function u and when you consider the composition, you know all how, for example, to get the equation of the composition. So here, if I consider some general process, which I can write as two parts. The first part is deterministic, and the second part is some stochastic. DW, it's a Brownian motions. Of course, when I am writing that in differential form, always you can think about the corresponding integral form to give the mathematical sense of this expression. I mean that I should integrate in time, and the integration in time is defined, and integration with respect to polynomial motion via the construction of Ito integral is defined. So this expression has sense. So if I compose my function u by f, I will, in the classical case, you will get only the first two terms, ft tu dt plus the derivative or the gradient with respect to u du. But in the stochastic calculus, you have some correcting term, which is related basically to the probability of the square, the bounded variation of the Brownian motions. So formally, when you are considering the square of du, you will neglect all the terms that come from the power greater than 1. And you are keeping only the terms that in that more or less in Taylor expansion, the term of order 1. This is what we do in the classical way. We are ignoring what happened after the second term of Taylor expansion when you consider the chain rules. But here, since you have something, the square variation is dt, you should take this in consideration. And this will give you the last formula, which we called Ito's formula. So if you are studying some PDEs or stochastic process, when you apply chain rule, you should always take consideration that you have some additional term and you should take care to deal with them. Of course, you can write all that in an appropriate mathematical framework by integrating in time, as I mentioned before. My written is always in differential form, but always think about the corresponding integral form. For example, if I consider the following process, du, which is the sum of two deterministic and stochastic parts, where h is, we have some regularity, take value in some Banach space, dl of some Banach spaces, and p take value in some Hilbert spaces. If you apply Ito formula, you will see that when you integrate in time, you have this expression, and you notice that this term plus p squared is some additional term that doesn't appear if you apply the classical calculus. Okay, I will try to give general form of some stochastic partial differential equations. In abstract form, if you consider Lyons-Gelfand trouble, basically you consider some separable Banach space, which is MP densely in some Hilbert space, and you can apply Riesz theorem to identify that with this DL, and then you have the duality with V prime. I consider this triply because it is classical when you are studying evolutionary stochastic partial differential equation. And of course, I will consider complete probability space. For the complete, I assume that all know what does mean complete, that I am considering all the set of measure 0 included in my sigma algebra. Then if you consider some one-dimensional Brownian motions, I will define some map from omega 0 to omega v, take value in R. Let's for a moment assume that my map is Lipschitz with respect to the last argument. And I can consider, for example, the following abstract form where A is some differential operator. You can, for example, think about Laplacian or P-Laplacian or any differential operator for the moment of order 2. We are starting with some initial data. Of course, your boundary conditions are more or less included in your Banach spaces. The classical example is the stochastic heat equations. So you see in 1D, if I consider the following heat equations, you have U, my heat distribution, and you have the second derivative with respect to U, and therefore I have some noise. I write this in this the stochastic heat equation in this form because it's totally legal in this case. Because for instance, if you integrate in time this equality, you will prove that this difference is absolutely continuous in time. Then you apply some classical Lebesgue theorem to prove that you can prove the existence of derivative almost everywhere. So this writing is legal. So generally people consider an integral form, but in this case, I can write that. So if you have the unsuitable assumption, for instance, P is Lipschitz, you can prove the existence and uniqueness of solution of this kind of problem. What is important to notice is the following. If I integrate in time, I will recover the first equality. Then if I take the expectation, meanwhile, if I integrate with respect to omega with respect to B and use the linearity of the integral, of course, I will recover that since the stochastic integral in Ito sense enjoy the property of martingales, the stochastic term will vanish. And I will recover the following equation for the expectation since the equation is linear. This doesn't happen for nonlinear equation, of course, but you see that if I start with some deterministic initial condition, then the mean of the stochastic problem solve the deterministic heat equation. And this more or less some link between the deterministic and stochastic, but unfortunately, this happen only for few equation, linear equation, and if we start with deterministic, of course. But you are interested in more general situations. I will show you some numerical example. So if you consider the following stochastic heat equation with some reaction term, of course, you have the following explicit solution. If you apply Ito's formula, you can prove that this solution solves this problem. So just to see, always it's good to see some pictures. So if you see in the middle, the diffusion of heat in some domain, but if you consider the stochastic or the randomness, here I am only simulating one path. So I fix omega and see the map, and you see the effect of randomness to my heat. Of course, if I consider the mean of that, I will recover the picture in the middle. Here, if I pick one point, let's say, for example, the point x01 or x0 you see here in the red color, the solution of deterministic, and you see here in blue color, the solution of stochastic. So you see, they are more or less behave the same way, but the stochastic has more fluctuations. Okay, this is what I would like to say about the Brownian motion. So for me, what I consider it generally some noise, which is only rough in time, but have some regularity in space. Generally QNR process or Brownian motion or this kind of stuffs. But of course, we can consider more general noise that depends on time and space. And the situation became very, very complicated if you consider a noise in time and space, since you can't give sense to your equation in variational sense, and you can give only sense in distributional sense. And this doesn't help to solve partial differential equation or stochastic partial differential equation. Therefore, you need to renormalize your equation since you have too much singularity. And for that, you need what we call the regularity restricted field theory, which is a very recent theory included by Martin Herer in 2014. And as you know, Martin Herer won the Fields Medal about his work about this theory. For instance, for the noise that depends in time and space, we can solve only some linear and semi-linear elliptic and parabolic problems. There are some recent results for hyperbolic problems and basically the wave equations. And the monotone problem, even in elliptic and parabolic, there are only some work in progress. So we don't know how we study general equations if you have noise in space and time. But I know very, very general noise. Of course, if you consider some noise with some regularity in space, you can deal with that. For example, some very general Gaussian measure and this kind of stuff. So during my talk in the second part, I am considering only a noise in time. So I will consider only a QNR process. Thank you for your attention. This is what I would say about the first part.
Okay, thank you, Yassine.